Okay, let's get started.
Yep. Way of getting there.
We are flying along, already done with our MA343 review. Right? So now everybody remembers everything that they had during MA343. Right? We, I've had a couple of questions outside of class on some of the confidence interval and hypothesis test things that we've been doing, and my intent on that is to be able to use your calculator. Just use technology to do the bulk of it for you, but also you should remember what a confidence interval is, how you build one, right? And remember what a hypothesis test is, what a test statistic is, and all that kind of stuff, right? So let me, I forgot to get the, how do I do this? Now, let's see. I have, oh, there, that's it. That's what okay. I need to get the active inspire thing going so I have a board to write on. But remember, just overall, when you do a confidence interval, how is a confidence interval formed? You start with what?
The significance level.
No, that's hypothesis testing. Okay, boy, guess. Start with your guess.
Your estimate.
Your estimate, that's right. So hopefully it's an educated guess, but it is your guess, your best guess as to what you think the population parameter is. So confidence interval, you're always trying to estimate some characteristic of the population, a parameter. And it's almost always a mean or a proportion. All right? Now, later in this semester, very soon in this semester, we're going to put confidence intervals on the slope from a regression line, on the variability around the regression line, things like that. All right? But from MA343, all you ever did were confidence intervals on proportions or means. Okay? So let's suppose we want a confidence interval on a mean. Here we go. So a confidence interval, CI for confidence interval, starts with a point estimate. So if it's a mean, that'll be X bar, the sample mean. If it's proportions, it'll be P hat, the sample proportion. So in other words, your point estimate is always that thing from the sample. All right? So if you're trying to estimate a population something, your best estimate is the sample something. So point estimate plus or minus what? Okay, the margin of error. And I call it MO, margin of error. All right? Now that margin of error has two components, and that's what Taylor was starting to say. The margin of error is the product of two things. What are those two things? Okay, it's not always a Z, but it's a critical value. So I'll just put CV for critical value, and then we'll talk about that in a second. And then times what?
Standard error.
What did you say?
No.
The standard error of the point estimate. Okay? I don't expect you to have the formulas for all these things memorized, but they're in the book. Right? So if you're wanting a confidence interval on a proportion, chapter whatever in the book will show you confidence intervals on proportions in the new book. If you still have your old book, then you'll know where it is better there, but you can find it easy enough. Right? So let's say it's a proportions problem. What's the critical value? Z or T? It's always one of those two. It's a Z. Right? For means, it's T. Okay? Then you have functions in your calculator that will give you those critical values. This was inverse norm. We talked about that one a little bit last time. This one is inverse T. If you have a calculator that has inverse T, not all of them do. The TI-83 that Brent's looking for right now will not have it. TI-84s, most of the TI-84s do have it. You can program it into an 83 pretty easily, or you can say, just give me a T-table for the test, and I can look it up. Right? I'm not going to review too much how you get these, but, well, I will a little bit. If we, let me add a page here. If you have Z critical value, that comes from the standard normal distribution. Do you remember standard normal, what that means? It has a mean of 0 and a standard deviation of 1. So if you draw it, it's going to be centered at 0, which means half of the values are negative, half of the values are positive. And halfway down the hill, we'll be out at 1. Right? 1 standard deviation is the number 1 in a standard normal. So 1 and negative 1. Now, if I want 95% confidence, you can figure out the critical value you need by using the inverse norm function as a percentile function. Right? So if you want 95% confidence, I'll draw solid lines and 95%. You want 95% or 0.95, and that turned out to look like a 6. You want 0.95 in the middle, right? So to figure out how to use the inverse norm function to get the critical value, you think, okay, I got 95% in the middle. How much is not in the middle? 5%. And by symmetry, half of that 5% is up here. Half of it is down here. And the inverse norm function or the inverse T function are what we call percentile functions. They return percentiles, which means what percent of the population is below that value. So all the way to the left. You don't stop here at the 95%. So inverse norm of what? This number plus that number, right? That's the percentile. So that's 0.975. My 7 kind of looks like a 2, but that's 975. And that should give you 1.96. Okay. Or you could enter 0.025 instead of 0.975, which is 1 minus it, which is just the area down in this lower tail. So I always say, well, you just enter half the leftover area.
And that's under, how do we get to the inverse?
Second function, and then vars. Above the vars button, it says DISTR. Right? So whatever confidence level you need, you can find the critical value for a Z critical value using this inverse norm function. You can also use a Z table in the back of the book. But I don't teach how to do that because everybody's got one of these calculators and it's a lot easier. If you have an inverse T instead of an inverse norm, it's very similar. Same idea on the number to enter here, but you also have to enter what? Degrees of freedom. So degrees of freedom for a T degrees of freedom equals n minus 1. Right? So n is sample size, degrees of freedom is n minus 1. Now if you got a 2-sample problem, it's a little bit different, but that'll be in the book. Okay? If you don't have the inverse t function, then you're going to have to be looking it up in a t table. Okay? So now, back to this. That'll give you this critical value. And then standard error, you've got formulas for standard error, depending on what kind of problem it is. If it's a means problem, and it's one sample, then standard error of x bar is sigma over the square root of n. Right? We did this last time a little bit. Instead of sigma, in real research, you're not going to know the population standard deviation, so what do you have to put there? The sample standard deviation. Remember, anytime you need a number from the population that you don't know, you estimate it from your sample, so use the sample one of those. If it's a 2-sample problem, then it's got the square root and the S1 squared over N1 and all that. You can look that up in the book. If it's a proportion, standard error of p hat. Remember what that one is? I know it's Corey, right? Yeah. I know Corey knows because we were just doing it. But what did you say?
P,
and then 1 minus P.
Over
N. Okay? Now again, P is the population proportion. If you knew what P was, why would you be bothering to try to estimate it from a sample? So you're not going to know what P is. So you're going to substitute in P hat. Right? That'll give you critical value, standard error. Multiply them together, you get margin of error. Add and subtract, and it gives you your confidence interval. Right? So your sample is going to say, in my sample, this parameter, or the estimate of this parameter is this one number. But I know there's some error involved there, so here's my margin of error. Add and subtract to give me an interval that I'm 90 whatever % confident it's actually in there somewhere. Okay. Good on that? So remember, in this MA343 worksheet, it's either going to be proportions or means. And then once you know that, it's either going to be 1 sample or 2. And then if it's 2 sample, you then have to make a third decision. Are those samples independent or are they dependent? All right? Now, in my MA343 class, I did not teach the dependent samples proportion one, so that's not going to be in there. But there is a dependent samples means one, but I don't think it's one that I assigned. But if it is that kind of a scenario, then remember you use the differences. Paired samples, you take the difference within each pair. Then you've reduced it to a 1-sample problem and you use this. But just look it up in your book for all the formulas that you need. You can, in your calculator, you can push stat, then test, and then go down that list and then try to remember, okay, now if it was 1-sample proportions, it's 1 prop z int, or whatever. If you're confused at which one it is, ask me. I'll help you. Okay? Okay, so let's move into what we're going to do for today. And that is the start of chapter 9. So this is the author's PowerPoint presentation, which I'm not going to, I only want it up here because it's got an example problem in it that I want to do, but I'm going to do all the stuff in here just on my own. But what chapter 9 is about is analysis of two-way tables. That's a little bit different terminology than what you probably had out of the MA340 book, but you did learn this in MA340, at least in my MA340, contingency tables. Remember those? Also called a two-way table. So contingency table is a cross tabulation. I guess I can't flip back and forth with that on. So a two-way table is a cross tabulation of two categorical variables. Okay, so if I have, this is the example I'm going to go through here in a second, coronary heart disease. And I can't remember whether it's yes and then no, but that's the way I'm going to draw it for now. And then they did a measure of the anger level of people. Basically, how angry of a person are you? Right? Brent would be at the high side. He's just angry all the time. So guess what? He's more at risk for coronary heart disease. So anger level is measured at 3 levels: low, moderate, and high. Then I draw a table that has 2 rows and 3 columns. So this is said to be a 2 by 3 table. This book uses the word contingency table, but they usually refer to it as a two-way table. Okay. Okay, and then you'll fill in with each cell of this table, you'll fill in with the counts from your study of where everybody falls. Now the way it works for this type of analysis to be valid is that each of the cells must be mutually exclusive. What? What does that mean, mutually exclusive?
They're in one, they can't possibly be in another.
That's right. If you have coronary heart disease, then you're going to be on the Y row. You can't also be in the no row. If you're moderate anger, you can't also be low anger. So it makes sense here, right? So these analysis of two-way tables take 2 different forms. And the chi-square test is used the same way for either of those 2 scenarios. One scenario is like this. You have a single random sample from some population, and then you measure 2 different variables on that same subject. You decide, do they have coronary heart disease? What's their anger level? Right? So you've measured 2 things on the same person from a single sample. The other scenario that also fits this type of test is where you have a simple random sample from different populations, and then you assess a response variable on those different populations. So I might say, well, let me take a sample of females. Let me take a sample of males. Now I'm going to see if they have the same anger levels. Right? And we all know the females would be on the low end, the males would be on the high end, right?
My mom would not fit that.
Okay? So either of those scenarios is okay, but and you use the same test, but you have to keep in mind, okay, how does this situation fit the analysis? Okay? Now, let me flip back over to this PowerPoint, and we'll get the actual table for this analysis that I'm going to go through, and we'll get some data in it. It's way down here apparently. Nope, there it is. Okay, so let me make that a little bit bigger. And I'm not allowed to write on that, am I? Nope. Oh, goodness, what did I do?
You just went forward and then.
Just by tapping it, it goes forward. So let me back up. Okay. And what I'm going to do is I'll get a marker and I'm going to copy that over here because I want to have it so we can see it at all times, but reuse the screen. So I've got CHD, yes, no, right? And then low, moderate, and high for anger. And read me the 53.
110.
Is 110 over this way?
Yeah.
Okay. 110. 27.
3057.
3057.
4621. 606.
606. Okay? Now, the question that we'll try to answer with an analysis of this table is, are those two variables associated? Is your risk of coronary heart disease related to your anger level? Or does it really not seem to matter? Okay? So the first thing we do is what I call the eyeball test. You look at the numbers and decide, does it look like your risk or the proportion who get coronary heart disease is different for the different levels of anger? And what would I need to compute to answer that question? The proportions. And what kind of proportions? Do you remember the name? They're called conditional proportions, right? So there's three kinds of distributions that they'll use that term in this section. Joint distribution, marginal distribution, and conditional distribution. Oh, there. So the joint distribution. Have I talked about my abbreviation method here with the little underscore N? That means shun. So distribution, right? So the joint distribution is the word and. Both things have to happen at the same time. So they have to have coronary heart disease and have low anger. There's 53 people like that, right? So cell count divided by grand total, where the grand total is the total number in that table, right? That'll give you the joint distribution or the joint probability of both of those things happening at the same time. Okay? So what do you think marginal distribution means, or marginal proportions?
Cell count divided by the column total.
Nope. That's conditional. What'd you say, Laura? That's what he was saying. That's conditional. Maybe I should jump to conditional. But margin, what does the word marginal make you think of? The margins of the table. So that over there you see the cells in the table. Let's fill in the margins. So the margins are the totals. So I get row totals here, and I get column totals here. So do those for me so I don't have to go over there and hit the
190, 8284 on this side.
190 and what?
8284.
8284.
First on the other side, 3110. 4731, 633.
633. Okay, and the grand total?
8474.
8474, and that's in. Right, that's the sample size. So the marginal probabilities are the row totals or the column totals divided by the grand total. Right? So it's probabilities for one of the variables completely ignoring, or another way to say it is summing across the other variable. So the marginal distribution of anger are the three percentages for anger summing across coronary heart disease. Right? So I just about wrote on it with this. Marginal totals are the row or column totals divided by grand total. Okay, so the marginal distribution of anger low, and I'm just using L, low is 3110 divided by 8474. And then you can convert that to a decimal or to a percent. All right? Somebody do that for me. What is that as a decimal? .367. Now, without writing it all out, moderate and high, moderate would be 4731 over 8474. Everybody see that? So what is that as a decimal? 0.558. Okay. 0.075. Okay? So you can see that more than half of our sample were in the moderate range. And then a little more than a third were in the low range. And really very small percentage were in this high anger category. Thank goodness.
Right. But you said that's no correlation.
Have we talked about correlation yet? Good question.
They're just looking at the percent of population that, or the sample that has.
Right. These are marginal distributions. This is no way ties it to coronary heart disease because it's summing across coronary heart disease. Right? In order to do that, I need to say what? Or I need to do what? Conditional. I need to find the distribution of coronary heart disease conditional upon what level of anger they're at. Before we do that, though, let's do the marginal for coronary heart disease. What's yes? 190 over 8474.
0.0224.
224. Okay. And the nose? 1 minus that. I can't do that in my head. 0.9776. Come on, you got calculators.
0.9776.
Okay. Okay. So around 2% of the study had coronary heart disease. The other about 98% did not have coronary heart disease. But now we need conditional distributions. Right? So conditional. And what's more of interest? The conditional distribution of anger level conditioning on heart disease or the other way around. The conditional distribution of heart disease given what level of anger they have.
The second one.
That's the second one, right? So you can always, not always, you can sometimes pick one of the variables to be what you would call your explanatory variable and the other one to be the response variable. So in this case, it makes more sense to think of, well, their anger level might explain whether or not they have heart disease. Not the other way around. Man, he got heart disease and became very angry. Right? So it makes more sense to go the other way. So I'm used to putting the explanatory variable as the rows and the response variable as the columns, but this book set it up the other way, and it doesn't matter. It's just that's the way I'm used to doing it. But so let's do the conditional distribution of heart disease conditioning on anger level. So there'll be 3 of those. Conditional distribution of coronary heart disease given or conditioning on anger level. So I'll write it as probability, but proportion. The probability of yes given low. And did we do this before about probabilities? Conditional? Okay, so the vertical line, it's not a divide symbol, it's a vertical line. What 2 numbers do I divide to give me this? Good. 53 divided by 3,110.
0.0170.
Okay? So what that says is if somebody has low levels of anger, they have a 0.017 risk of heart disease. Right? So about 1.7% of people in that category have heart disease. Let's see if the risk increases as anger goes up. So moderate is 110 divided by 4731. Everybody seeing where I'm getting numbers? What's that as a decimal? 0.024. Give me one more place.
I rounded, so 0.023.
Now I got to erase.
Yeah, I know.
It wouldn't be so bad if I could erase with my finger. But
0.0234.
And you rounded to a 4?
0.0233. And off.
It's 0.0233.
3.3.
If you round.
So you rounded incorrectly a minute ago. Okay? Not that it makes a whole lot of difference. We're talking about risk here and the nearest 0.1%, but we're statisticians. We have to be anal about stuff like that. Okay, now finally for high, we get, what are my 2 numbers to divide? 27 over 633.
0.0427.
Okay, now, eyeball test. Jeremy, is this evidence of an association? Are you Jeremy? Don't listen to her. She's wrong.
I know that you're supposed to say, okay, things are going up, but these are such small numbers.
That is a great point. And it's almost like I paid you to make that point right then. That's a very small increase in risk, right? But this is the way disease works. Most bad diseases are fairly rare, so the probabilities are low. But look at them relative to each other. Going from low to moderate did what? It nearly doubled it. Right? It nearly doubled it. And then going up it nearly doubled the risk again. So high to low, take the quotient of those, 0.0427 over 0.017. Do that on your calculator, what do you get?
I would also want to...
No, hang on to that. Keep saying it, but just do that number first. This is called relative risk, and it's a term that they teach in this book in Chapter 8. It's the only term in Chapter 8 I'm going to make you know, but you need to know relative risk.
2.5.
So high over low equals 2.5,
1176.
and 1 is enough, right? So the relative risk of high relative to low is 2.5. The way to interpret that is your risk is 2.5 times higher of getting heart disease if you're in that high anger group. So do what you can to get yourself out of that group. Go to anger management training, learn to meditate, do some yoga, and you can decrease your risk. Right? So the numbers are small, but relatively they're going up fast. Right? Now, what was your thing you were going to say?
I would also want to look at no in these and then see what that looked like to see if this really says what you're kind of assuming it says.
Okay. Now, if I did that, there's 3 more conditional probabilities to compute. The no's, right? So the probability of no given low, no given moderate, so on. How are they going to relate?
1 minus that.
There'll be 1 minus these. And so you really don't need both. Let me get a blank page here. Sometimes looking at the numbers isn't enough for me. A picture's worth 1,000 words. So we do what's called a side-by-side bar graph. Right? So I'll go low, moderate, and high. And then I'm going to draw a bar for each of those percentages. And you want to do percentages here and not the actual counts. I don't want to put 53 versus 110 versus 27. That's misleading. Because the 110 looks way higher than the others. And high looks like the lowest one. But you need to plot the conditional proportions because that's what's comparable. Right? So the low was a bar that was up to 1.7%, right? 0.017. So let's just put it on there, 0.17. And then the moderate was about, but not quite, twice as high. And that was 0.024. Is that right? I'm going from memory. Oh, actually, I got it. 1, 2, 3, because Nathan can't do it in his head. See, I'm blaming him. There. And then the high is about, but not quite twice as high as that one. So 0.043 if I go to 3 places. Okay? If there was no association, what would you expect to see in this graph?
Hopefully the same.
They would be about the same. They're never going to be exactly the same, but I saw several people do it with their hands. Okay? They're pretty flat across there. They're all roughly the same height. But if you see a trend like this, then, oh, that's evidence. Right? Yeah.
So, because you used to do, or you still do pharmaceutical stuff.
Uh-huh.
Like, what if you see that it's actually higher in the low than medium?
Like it's U-shaped?
Yeah.
That does happen sometimes. Not necessarily with a scenario like this, but you'll see that there's an optimal place where you want to be. Right? And
still consider that an association?
Yeah, it's still an association. The definition of that word, association, is if values of one variable, coronary heart disease, tend to occur more often with certain levels of the other variable, that's association. So it doesn't say it has to be in order. Just, lower values of coronary heart disease tend to occur most often in the moderate than the other two, then that's still association. right? When we do linear regression and that kind of thing, then that's forcing a certain pattern to it. But just association, that word is not, doesn't matter which one it is, which group is different, just that at least one of the groups is different. Okay? All right, so now we're going to do a little exercise. Remember, we haven't talked much about hypothesis testing yet when we went through that review. We did the confidence interval stuff. But remember, for hypothesis testing, you have a null hypothesis and you have an alternative. Usually, it's the alternative that you hope to prove, but you do all the work assuming the null is true. So, if the null is true, what's the probability that I could get data like this? Right? And that probability is called the p-value. I drilled that in your head, didn't I? So the p-value is the probability you could get data like you observed, or even further from the null, if the null is true. Right? So the way this hypothesis test will go for a contingency table or a two-way table is known as a chi-square test. So it's the Greek letter chi squared test. And often they'll spell it out, so it's CHI square test. Okay, so the chi-square test. And it's a test for association, or equivalently, test for independence of two categorical variables. I'll say between two categorical variables. So the null hypothesis, we tend to just write the null and alternative hypotheses as sentences instead of mu equal this, or mu1 equal mu2, or p1 equal. You could do it with p's, but the number of p's in your statement depends on how many columns there are in your table, how many rows there are in your table, so we just say it like this. The null is there is no association between, and I'll say it in a generic sense, the row variable and the column variable. So whatever those two variables are, right? Between the row and column variables. Now on a test, if I ask you to write out the null, I don't want you to say row and column variables. I want you to say between coronary heart disease and anger level, or whatever the scenario is. So do it in the context of that particular problem. Right? So what do you suppose the alternative hypothesis is? There is an association. So you just leave out the word no. And I would let you get on a test and stop there rather than write out between the row and the column variables. But technically that's what it is. Okay? Now, hypothesis tests always work the same way. We formulate the null and alternative hypothesis, and then we compute some kind of a test statistic, and then we see how extreme that test statistic is compared to what we would expect it to be if the null were true. So if there's no association, how likely would it be to see this?
It's not likely.
Probably not very likely. I would expect to see it to be flat across there. Right? So the way this statistic, the test statistic works, let me come over here. This is what's called the observed counts. This is what you actually saw in your study. So down here, let's make the same table, but let's fill it in with numbers that we would expect to see if the null were true. So expected counts. I'm not going to put the column and row headers. It just matches up. But you do this assuming that the marginal totals are the same. Okay, so you're assuming that you took a sample from the population. And in that sample, there were 190 people that had coronary heart disease. The rest of them didn't. And in that sample, there were 3,110 people who had low anger, 4,731 that had moderate anger, and only 633 that had high anger. Right? So these are fixed numbers. Now, fill in numbers in the table that make the null true. But the catch, you got to get the right column totals. You got to get the right row totals. How many tables do you think you could make by filling in numbers that add in the correct directions both ways? How many different tables do you think there are?
A lot.
A lot. There's a lot of those tables. Because this is a really big sample, right? For instance, I could put 3110 right there and 0 right there, and I get that total right. As long as I make these numbers work up. Oh, wait, I got a problem, don't I? I can't do that because that's summing too high. So that table won't work. You see the idea? There's tables that work and tables that don't. Well, maybe I could put all 190 of those there, figure out what's left here, right? And then this would be 0 and 0. That'd be a table that worked. Right? I want the one table that makes that null hypothesis correct. Okay, do it. Figure it out. So we got this picture. If the null is true, you told me this would look like what? It'd be flat, right? So fill in numbers so that I get that. So they are exactly equal to within 4 or 5 decimal places.
So I'm saying 190, 3, put them all in.
Say it again. 190 divided by 3 and put that number in each of those. Is that going to work though? Because remember where the heights of those bars come from. The heights of those bars come from the conditional proportions. These totals are fixed. So I need whatever number I put here divided by that number to be the same as this one divided by that one, to be the same as this one divided by that one. So I can't just divide the 190 because these sample sizes are different. This is a good thought. Yeah.
Start by taking the mean proportion.
Ah, good. So marginal proportions, right? So what is the total proportion of people who got coronary heart disease? The marginal distribution of coronary heart disease.
It's 0.0229.
Okay, so the probability of a yes, right? Not conditioning on anger. The probability is well, let me write it as a fraction. 190 divided by 8474. And you said that's 0.02 what?
0.0224.
422. We'll use lots of places here. So that's what I want each of these to be. So in other words, I want each of these conditional proportions to be that. So what number do I put here so that that number, call it x, call it x1 because it's first column, x1 over 3110 is equal to 0.022422. Solve for x. I know it's a tough algebra problem, but you guys are math majors, right? What is x1? 69.731. Right? And we're going to allow decimal places. Right? So 69.731. Do the other two.
Next one's 106.078.
106.078.
The other one's
14 point 1928. Let's call it 193 because I've been keeping 3 places. Okay? Now, you could do the same thing for the next row, but you could also do what? Subtraction. They have to add to 3110. So take 3110 minus 69.731 and you get that number. Go ahead and do those. 3040.3. Give me 2 more places.
269.
269.
And 4624.92.
4624 point what? 924. I'm keeping 3 decimals on each of these. And then this one?
618.807.
807. Now, can you confirm that each of those adds up to what it's supposed to add up to? What about going this way? Yeah, 69.7, that's about 70. This would be about 176. And add 14, it'd be about 190. Right? So this is the one table out of all of the possible ways to fill in the numbers. This is the one way that makes that null hypothesis exactly true. Right? So in other words, this table is what I would expect to see if the null were true, but this is what I got. How different is this from that? We need a statistical way to compare them, not the eyeball test. The eyeball test is important. That should be your first step. But, right? And before I do the test statistic, this is 0.0224 on all of them. So this is distribution if null is true. Right? So that's the distribution if the null is true. That's the distribution that we saw in the data. How similar are they? Well, they're not real similar. We need a way to compute that. Okay? So the way it works, the chi-square test statistic goes cell by cell through the table and says, okay, in this cell, how far away from the expected value is the observed value? So you take the observed, I'm just going to use O for observed and E for expected. O minus E, you're going to square it to get rid of the negative sign. And I'll say more about that in a second. And then standardize it by dividing by E. You're going to do that for every cell of the table, and then you're going to sum them all up. So I'm just going to write it this way. Sum across all cells. Everybody knows the capital sigma means summation in mathematics, right? Okay? All right, so I want this half of the room. I'll tell you what. Let's do it this way.
By the way.
Is it time to quit?
Yeah.
Man, I'm just getting revved up. All right, we'll pick up there next time. Sorry about that.